Joyce.
Thanks, guys. Yesterday, we need like a hand function on the smartboard.
Oh, if you do like full screen like Crawford does, you could do it.
Not really do it, but see it. You mean entire page?
I think the other way you had it was fine, but it's okay. It doesn't matter.
Yeah, but I can't touch this side of the board and scroll it down. I'm going to do this side. Okay, yesterday we went ahead and started talking about parametric equations. Parametric equations, what's the parameter?
T.
T, or
Theta.
theta. Those are the two most common. But technically it's any third variable that both x and y are dependent on. Hence why we're going to have two separate functions, one for x, one for y. And it gives us a path. Question. If x and y are defined separately, can a parametric equation, set of equations, there are two of them, can parametric equations be functions while still failing the vertical line test?
Yes.
Why?
Because they're not in rectangular.
Okay, they're not in rectangular, but why, specifically? What makes a parametric set of equations a function?
They have a certain output for input.
A unique output for each input. But what's the input now? T. So at one time, you can only be one place. But, if we think about like a normal function that would fail the vertical line test, I don't know, something like this, right? If it's orientation, starting at an initial point, for instance, and then following this path at time 1, for instance, we'll say that the particle is here. One position, 1x, 1y. Time 2, it's here, 1x, 1y. Time 3, it's here, 1x, 1y. But wait, what about, but it's at two different times. Doesn't matter if it's the same x. Does that make sense? So the whole definition of a function kind of changes now that we're thinking about parametric equations being functions. Now still technically when you hear the word function, you're probably still thinking function notation, x and y coordinates, y is dependent on x, but just kind of thinking through, now we're going to be able to fail the vertical line test while still in essence having the idea of a function, because each time we'll only have one location. And if at one time you're at two locations, we have bigger issues than parametric equations. So, moving on. Yesterday we talked about initial point and terminal point. One key idea that you have to hold on to, will there always be an initial point and a terminal point? No. First of all, it's only when you have a closed interval. And second of all, technically, it's still based upon, closed interval or not, it's based upon the nature of the function. It's based upon the nature of the function. But when you have a closed interval, yes, there will be an initial and terminal point, or there should be, unless there's some sort of discontinuity in between. We talked about tables. You have that. Yeah, you're going to need to choose t values, and then you're going to find x and y values by plugging in. Orientation is shown by shows direction that the particle, because this is used in particle motion a lot, or maybe not even just particles, but like motion in general. It shows the direction of the movement along the path or the plane curve with arrows, like you kind of just saw me do. By calculator yesterday, we wrote down mode and parametric mode. What's new about the quick note on graphing down below? We just said only graphs stated on a closed interval will have an initial and terminal, but what does the quick note say?
That our calculator might have an endpoint and a start point, but that doesn't mean that the function itself has an endpoint and start point.
Right, so let's quickly go to our calculators because I want us to work with them because we have to be, remember, proficient at our calculator as well as by hand. Two approaches. So let's go ahead and with our calculator, let's see what on earth this quick note is saying. It's saying whether or not the problem gives a closed interval, whether or not you put a closed interval in, like restricting it like piecewise functions, booleans, using the division sign to make a graph only have or graph for certain x values. Without that, your graphing calculator, according to this quick note, is going to stop and end on its own. But why? I want you guys to go ahead and start in your calculator. We'll go back to by hand. Start in your calculator. How are we going to graph it? Use parametric mode. Shortened to be PAR, P-A-R. If you guys look at the problem, there is no closed interval. There is no set or range of values for t. So theoretically, no closed interval, this thing should go on forever. Right? You guys do it. Don't watch me. And if you don't have a calculator, look over someone's shoulder. Non-awkwardly. No. Whoa! X1T, Y1T, it's like they, oh, know what parametric mode is.
What is it? X equals t or e1 minus t squared.
Hit the variable button, that's the T. Used to be an X, now it's a T because we're in PAR mode. I'm going to do zoom standard just so we're all in the same place.
It's going under par.
What? It's like part of a downward parabola. So there was an initial point. Did you guys watch the way it graphed? It started here and it graphed down.
Yeah.
As time increased, wait, time increasing. How does your calculator deal with time?
1, 2.
How did it always graph? Where were the restrictions as far as how to graph, what to graph, and what intervals to graph? Where is all that information found? Window. This is right. What's new? T-min
T step.
and T-max and T-step. Very similar to X-min, X-max, and X-scale. Those are the units. But what's different with time? Is time an axis?
No.
No.
It's not. It would be like a.
Time's a separate variable. Go ahead, Jordan.
Is it like sorry, for lack of a better word, is it like a parameter? It's like a something to describe how x and t will come out.
Yes, it is.
And that's how like it's programmed into the company.
So the calculator is using this in its hidden calculations of the programming itself.
Okay.
So t is being plugged into basically these equations, but you're not actually seeing time in the graph. What you're seeing is when time is plugged in, what occurs. So, kiddos, go ahead. Now we have the calculator graph for just a second. I wouldn't sketch it quite yet, but we do have this calculator graph. This was with zoom standard. I'm going to take the graph. I'm going to take the zoom standard, the standard window. Did any of you, I apologize, have a different T-min and T-max than 0 and 6.2831 P5?
Yeah.
What'd you have?
Mine has 0 and 360. Why? I have no idea.
Go with
It
your
also
mode.
doesn't look.
Wait, hold on. How does 6.28 something correspond to 360?
Radian.
2 pi in degrees. So I'm guessing, Amanda, degrees, yeah?
Yeah.
What are you guessing I'm in?
Radians.
Okay.
So it doesn't say also. Wait, but also the graph looks different. Mine goes straight. It doesn't curve.
Wait, really?
Yeah.
And you're in zoom standard?
And it still says 360. Yeah.
Try and maybe zoom 6, maybe.
It is zoom 6.
Oh, yeah.
What on earth? Okay, that's weird. I didn't expect that. And you're in degree mode, right?
Yeah. Normal flow. Radian. This is also Isabel's calculator. So, I mean, it's the exact same calculator I used last year, but I don't know if there's anything you guys might have done last year. But
You know what? Hold on, pause. It wouldn't make a difference if we were using strictly trig functions, if the t was strictly in trig functions. Because if we're in radians, t plugged into sine, cosine, etc. for radians will be the same as plugged in for degrees. The problem is, are we plugging t into any trig?
No.
No. So when mine for t starts at 0 and goes 0.1, 0.2, 0.3, I don't actually have the increments that it goes, but when it starts plugging in 0.1, 0.2, 0.3, it's getting a lot of data points, it's having a very clear picture. But yours, by nature, since there is no trig, since you're going degrees, first of all, you're taking a t step that's a lot bigger. So you're going probably like 5s or 3s or something like that?
7.5.
7.5. So you're taking bigger steps, meaning you're only plugging in 7.5, 15, 22.5, etc. So you're only getting little bits and pieces, and the calculator is just connecting the dots. So when it connects the dots, think about if this is like 0.1, 0.2, 0.3, I have all this, but yours would just like whoosh, go straight to. Does that
How
make
would I
sense?
change that?
I would go radian and then zoom standard.
Okay.
So if we're doing parametric, and this is a word to the wise, if we're doing parametric and there is no trig, it's best to be in radians and then zoom standard.
Alright.
Okay. If there's trig, technically it doesn't matter, and every now and then it might be easier to be in degrees, but I would still, we're in calculus, right? I'd still probably start in radians and see where it goes from there. Come back. What if you were to graph by hand?
T-table.
Okay, we do a table, right? So I'm going to go ahead and make this a little bit lower. Set up a table with t's and x's and y's. With t's and x's and y's. Now, we get to choose, they don't give us a closed interval, we get to choose what t's to use, right? Now hold on. If they don't give us an interval, should we necessarily start at 0?
No.
Not necessarily. Now if it's in the context of a word problem, could we have to start at 0?
Yes.
Yeah, because it could be the initial. But we could be talking about relative to a certain time, but something was moving before that certain time, so we could have negative time in essence of what was it doing before the benchmark that we're looking at. So there are some places where negative time might be useful. But if we're doing it by hand, and if there is no closed interval saying start at 0 or start at some other point, we'll probably do something like, I don't even know, like -3, 0, 3, 6. We'll just do that for now. Or -2, 0, 2, 4. Just kind of keeping it basic. Doesn't always necessarily give you the best picture, but we'll see if this is sufficient. Once again, small numbers, hence why radian is good. Plugging in -3, 2, all we have to do is go back to our equations. What point, what location is this particle, is this thing, is this object at when time is -3? X value of -3, y value of -8. Good. So we go 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. Okay? There's our initial point, at least for our table. Plugging in 0.
1 or 0 and 1.
0, 1. Plugging in 3.
-8. Or 0 and 3 and -8. I'm sorry.
And then plugging in 6.
6 and -35.
That's -8, 16, 24, 32-ish. Now, from our table, if we were to graph what we just saw, be careful, we're making lots of jumps in between, and with calculus AB we learn with tables, we have to be careful of those jumps. But is this a continuous function? Yes. Is it a parabola centered at 0, 1? We think. We'll see how to check that in just a second. But how would I show or indicate the orientation of this parabola?
Arrows.
So we'd say, okay, we started here and we're going and we're going. Now technically, does my table have an initial and a stopping point?
Mm-hmm.
Yeah. But technically, according to what they stated, does my set of parametric equations have a stopping and ending point, or starting and ending point? No. So technically, we keep going after this point. And technically back here, we'd say that we were coming, right, from before, and we'd say it's just in general the parabola, from -infinity to infinity for t's. Now think about that, think about our table, now think about your calculator. Why is the calculator always going to show an initial and terminal, whether or not that's actually the nature of the functions, or the equations? There is no initial, there is no terminal, there is no closed interval. It's
Are they always
infinite.
going to be like a reflection? So it's only going to show half of it?
Not necessarily. It'll always show a part of it. Sometimes it might show all of it if it gets the entire path, and then like if it's circling, if it keeps on circling. And we'll see that in a second. What from our table made it look as though there was a starting and an ending?
Where we started.
It started plugging in. We started plugging in -3, stopping 6. According to the computer programming in your calculator, it has to start somewhere. And it has to end somewhere. So when you look at your T min, T max, what would happen if we went back to -3? It would show it. Does that make sense? So we can see as much of the graph as we dictate in the calculator itself. We'll see another graph in just a second, but first of all, how can we make sure without using our graphing calculator that this is a parabola centered at, I apologize, with a vertex at 0, 1?
We could
Get rid of the parameter. How do you get rid of the parameter? Eliminate. Eliminate. As you guys set this up, I'm going to go ahead and copy down the equations from the page before, and we will use them as an example of eliminating. Now, technically in your homework, in section 1.4, I do not believe they actually use the terminology eliminate the parameter. However, our brains don't think parametrically. We've been trained with x's and y's whenever we're thinking about functions. We know what y equals x squared looks like, hopefully. We know what y equals absolute value of x looks like, hopefully. We know what x squared plus y squared is 9 looks like, hopefully. Circle radius of 3. What's more of a struggle when things start getting defined parametrically. It gets a bit tricky. So I'm showing you this whole eliminating the parameter, technically a pre-cal idea that I covered in pre-cal when I taught it. Not all pre-cals do, especially summer ones. But allows you to take parametric equations, which are always split up, x equals y equals, and think about them rectangularly, which is like normal function mode, to get the picture, not the timing, not even the orientation. The picture itself, the path, doesn't show us that. We have to look at the t's at the times, at the parametric equations for that. But it does help us with what the path should look like. So, to eliminate the parameter is basically just to eliminate t. So, in essence, we could say that it's disregarding time. Is there a better way of saying disregarding? Regardless of? Oh well. Either way. I already started writing. Huh? In lieu of? Not in lieu of, not specifically. I'm not really substituting, I'm more just saying, let's forget time for a second. Let's forget how fast an object is going. Let's forget where it is at certain times. Let's just say, hey, what is it traveling on?
I mean, independent of.
Oh.
Then we have an independent variable.
Yeah, see, then we could say independent of, functionally speaking. Okay. Isolate t and x of t, then substitute into y of t. It's just a simple solving problem in the sense of we have a system of equations, so solve, kind of. This one's kind of easy because solve for t, isolate t. Well, we already have it isolated. T equals x. Then we make a substitution for t. This can lead us to, therefore, y is equal to 1 minus x squared. Wait, 1 minus x squared? What is that? A parabola facing down, up 1. Were we right? Yes. Technically, are the parametric equations like the graph I just showed? No. Not exactly, because there shouldn't be arrows facing 2 different directions, because something can't be going 2 directions at once.
Okay.
That's what I was thinking.
Can it?
I don't know. Probably not. But probably.
In
Not
space,
2 opposite
yes.
directions at once. One object, if it's being, like, exploded and then it's ricocheting, that doesn't count. But the path can be this, right? This can be the path. It's not necessarily showing the movement of the object, but the path itself, 1 minus x squared, no big deal, there's the path. But the parametric representation of the object actually moving along would be better demonstrated with our orientation arrows. Does that make sense? Let's keep going. Woo.
Example.
Why is this a circle?
Because there are trig.
But not all trig have circles.
Square it.
Well, I guess because
You can square it.
Because I guess if you
eliminate the parameter.
How do you eliminate the parameter for functions with trig?
solve
Solve for t, x over 3 cosine inverse. I don't want to plug in cosine inverse to a sine function, right? There's a creative way of trigonometrically, or eliminating the parameter with trigonometric equations. Usually involves squaring both sides for eliminating the parameter, and then using, I'll just say use, square both sides and then use trig identities. You're like, what? Some of you are like, oh, I kind of remember this, it was weird. Some of you are like, I've never seen it, please keep explaining. Okay, so, instead of solving for t, hold on, first of all, do all of us realize if we were to solve for t and plug in, we'd have a nasty cosine inverse in the sine function? Ugh. So a better way to eliminate the parameter would be, this is kind of outside of what the example is actually asking. They're not going to specifically say eliminate the parameter, but this is how we can figure out what the picture is without just memorizing all sorts of randomness. We can think, if only cosine were squared and sine were squared, maybe we could do something. Well, how can we get it to be squared?
Square it.
And to make it a little bit more strategic, since we do want to be getting the t at least somewhat isolated, I would still divide by 3. For one equation. Divide by, oh hey, it's 3. For the other equation. And here's the idea. Get the trig by itself, square both sides, and then say, I'm allowed to add equations together, subtract equations, divide equations, as long as I do it to both sides. How can I get cosine squared and sine squared
Well,
to cancel out?
They both add up to 1.
You equal 1.
When you add them, it equals 1. Now what does that mean? If I were to take cosine squared and add sine squared, the next step would be 1. But what could I say is on the other side? Who is cosine squared?
X cubed, or x over 3 squared.
Who is sine squared?
Y over 3 squared.
Now you're like, so I'm supposed to know what that is? Kinda. But maybe, just maybe, if it's been a while since you saw conic sections, it might be a little nicer if we moved the 3 squared to the other side. And then say, oh, it's really just a,
Circle.
with a radius of,
Are we gangsters now?
kinda.
What?
Now hold on, wait, but I need my orientation.
Oh, here we go.
Oh no!
Wait, and they gave me a closed interval. And I need my initial and terminal points. Oh, maybe just initial? Find the initial points. Struggle.
Just plug in 0 and then 2 pi.
Exactly. We figured out it's a circle. That's the easy part. Now let's just go ahead and figure out just from a quick table, by doing just a few, what's going on. Start at the beginning point, 0, right? What's cosine of 0?
Well, 1.
1 times 3 is 3. Sine of 0 is 0. So where's this puppy starting?
3, 0.
Here's the initial point, right? Now you can probably guess, but let's go ahead and just make sure. If I plug in pi over 2, just because it's easy, cosine of pi over 2 is 0. Sine of pi over 2 times 3 is 3. So now I'm at,
0, 3.
so which way am I going?
That way. We're counterclockwise.
Counterclockwise. Now where's my terminal point? We can probably guess if it took 90 to get 90, then 3 pi over 2.
2 pi.
Oh, I'm saying it wrong. Pi over 2 pi, 3 pi over 2, and then 2 pi. So it's just one full rotation. Now, on our calculator, quick question. What if, do we have like a minute left?
Yeah.
Struggle. Are we done? Oh, we're done. In homework tonight, let's do this first. Let's get rid of time. In homework tonight, you might, by doing some exercises, find some special parametric equations. For instance, maybe something to do with ellipses. We already saw maybe kind of what circles look like. And you might see something with lines. I have tried in homework to not really give you tons of extra that doesn't really apply to what we're going to be doing. There are things in homework problems that we're skipping that has to do with parametrization, whatever, that word, where you have to make up your own parametric equations. That's not the point of homework. The point of homework, can you deal with parametric equations in your calculator and by hand? Let me show you one cool trick though. What if we were to do, for instance, we saw something go around the circle once, right? But what if it was 0 to 4 pi? It would go around twice, but how can you tell in your calculator if something's going around twice or not? Because isn't it just going to retrace? No big deal. You could change the window to make it, instead of 0 to 2 pi, go to like 4 pi instead. But let's go, I'm going to do 0 just because that was like the initial in this problem. Wait. If you go here, go back. There's this little option. There's like bold, there's dash, there's a little circle with a little tail on it. And then when you graph it in Zoom Standard, you're going to see exactly how many times it goes around. Give me your focus on the way out, and I will see you tomorrow.
Oh, it's cut.
Alright. Cool kids, are we good?
We're great.
We're great. Section 1-4, you didn't even have to get into polar yet. We'll cover that entirely tomorrow.
So homework is actually due tomorrow.
Yeah,
Homework is due tomorrow.
sadly.
Actually. Oh, well, at least we all know now.
Yeah.
Bye, guys.
I'm gonna text it in the group chat anyway so I can actually get a response. Roberto, is this yours?
Roberto, do you have a water bottle?
It's not mine, I found it.
I don't think so. No, you want?
There we go.
It's the constant.
Hello,
Yeah, how's it going?
how are you?
Doing all right. How about yourself?
Good.
Staying out of trouble making life choices?
Yes.